So it has appeared to me that there's this puzzle. So I'll try to see whether I can solve it. I mean, the community success rate is about 20%. So I'm not sure whether this would work. But, let's go. All right. Okay, so let's see how this works. Okay, hidden fortresses are placed on a size by size grid. Okay, joined together from a grid of size row and size characters. Okay, so this is the input, and then you get strings. Actually, this looks quite a lot like Clash of Code, right? You get strings over here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this probably is like 2, 1, 2. Okay, so like A, B. Okay, so O is a fortress and dot is not a fortress. All right. So what are the numbers? The numbers, you are given the number of fortresses that share the same row and or I care about. Yeah, today I try something different. I try to see if I can solve this. Yeah, maybe later towards the end, like after half an hour of trying and I'm failing this, then maybe we can do Clash of Code. Have you tried this puzzle? This is something like, those tatami kind of solvers. You need to solve a row and a column. Hidden fortresses are placed on a size by size grid. You don't know their number and you don't know their locations. Each cell of the grid you are given the number of fortresses. Yeah, I haven't solved this as well. Yeah, but I saw two of my friends who have solved 100%. Look at this, Murat and how do I pronounce this? Murat. I think I can solve it. Let's try to see whether I can solve it. Okay, a size by size grid. Okay, you don't know their number and you don't know their locations. Yeah, actually hard problems are quite difficult. Yeah, so let's try to solve the 3 by 3 case. If we cannot solve the big case, we solve the small one, alright? Yeah. Because the biggest is 31 by 31. Okay. Yeah. Let's see. Those numbers are joined together in a grid to form a grid of size rows and size. I still a bit confused with what they are doing here. What's this number here? Okay, this is number of row and column. So this guy here has two. So here and here. This guy here has one. Okay, because there's only this row. Okay, it appears to me like the minimum number here might represent the number of uh, like 322. You take the minimum here will represent the number in that row itself. Okay, and you take the minimum across this column, it will represent also the number across this the number of O's as well in that row. Yeah, because I mean provided that there is hmm, I mean, in the end, the last part will definitely be some form of logical thing because you cannot solve it by simulation. 31 by 31 is too big. Okay, let's see the supposed output for this. Okay, so there's this LMNOP, which means, oh, I get it now. I get it now. Okay, I get it now. So it means that if we have this, okay, this actually corresponds to the ID index. Okay, so let me just put this over here. So like num count equals to this. Yeah, okay, maybe I expand this a bit. Yeah, so this probably refers to the index. So it's like if it's zero, it means there's a zero number here. Okay, all right. So for each row, so in the end I need to come up with an array. Okay, let's use numpy then. Import numpy as mp. I think Python should work for this. I hope because if it's a logical puzzle, I think if just a simple if else rules, maybe numpy might work. Yeah. Okay, so I create my uh, fortress. Maybe we call it fortress equals numpy dot zeros. Okay, let's see how do I define zeros. Np dot zeros. Numpy dot zeros shape. Okay, I need to put a shape here. I dot zeros, and the shape will be given by size. Yeah, something like this. So this will give me, I get the size input like that. Okay, let's print out the fortress now. Okay, I just want to see whether I can print out a full sum of zeros. Okay, so I can print out the full sum of zeros already. Let's see. If I want to get like 212, 322, okay, how do I do this? Okay, I need to get the minimum over here. So this will need reference from this num count, and then we can just take this dot index. So okay, basically I just need to convert this into cell count, and then this will be size also. And then over here, uh, cell count I, okay, will be equals to, okay, input, okay, x dot num count dot index x for x in input. Okay, and then maybe we print out the cell count at the end just to make sure that I convert this into a list of numbers, which then we can proceed to do some operations on. So that is indeed what can be done. Okay, so this is indeed what can be done. So we have done all this in terms of the yeah, we've converted all this back into the number of, what do you call that, number of elements, I guess. Okay, so let's see. Okay, so we have this. Now I just need to find out exactly where it is in the fortress itself. So prints fortress I. O dots. O dots. So it will be a dots like that. Dot O X for X. I think there might be easier way to do it, but I just want to see fortress I. Oh, actually, I can just make this zeros and ones. I mean, I can make this O's and dots. I'm not too sure. Yeah, but if you want to print out the fortress like that, dot O X for X in fortress I. Let's try this again. Um, okay, I somehow don't seem to get. Yeah, I can just do an easy way of doing it. It's like that. Yeah, we could just print out the output like that. This just basically converts string indices must be integers. So my fortress I is not an integer. Okay, I guess I'll just do it in a easy. Why is it not printing out? String indices must be integers. Isn't this an integer already? Fortress ij. I'm supposed to do like this, right? Yeah. Oh, I know why already. We converted my 0 into a float. That's why. Okay, so now everything is a dot dot dot. Very good. So now I can proceed to just change my fortress. Okay, one way to do it is because this tells you the row and column counts here. So you know already that each of this row and each of this column, okay, will already have like a certain configuration limit. Okay, one way is to just brute force and the get a matching thing that matches all these constraints here. So it's like, yeah, one way to do it is I could just like plug in an O here and then plug in an O here, so I can do like flat fill, and then like the moment I reach somewhere here and I realize that it doesn't fulfill the constraint, I will then restart. Yeah, then this will be a depth search of depth 9, so I can just do an O or dot, O or dot, O or dot to just make sure that this constraint is filled. Or I can just generate for each of these cells a possibility of two potential options, is either O or dot. So I can generate two, and this will be 2 to the power of 9, which is about 5, 1, 2 different possibilities. And then I just check whether this works. But I think all this will be too slow. Okay, because later on we have a 31 by 31 grid, which will mean that you need to check this 31 by 30 to the power of 31 times 31, which is a huge number. There must be an easier way to do this. So one way I can see is that I can take the minimum number for each of this. So if the minimum number is a 0, then we are in good luck. Okay, then we can output that entire thing as a dot dot dot. Okay, if not, if we do this, we get a minimum of 2. Okay, then we can basically fit this as 2. Like you can do a permutation of 2 O's here, and then you can also do a permutation here of 1, because it's the minimum here. Yeah, so if let's say we have cells with 1, actually we already solved the position, okay, because if there's only 1, it cannot be on that cell itself. Or okay, let's see, if over here there's a minimum, the minimum of the row and the column shouldn't contain anything. Yeah, so over here is a minimum, right? So we can start by the minimum and start doing stuff from the minimum itself, like start doing from here 0. If it's 0, it's definitely a dot. And then we go on to 1, 1, and we go on to 2, 2. So over here 0. And if we go to 1 here, 1 must be a O. Okay, I'm just thinking whether or not this really holds, because if it's like over here, all these are ones, okay, which means that in the row itself it must be uniform. So if let's say we start with 0, you see no zeros, okay, then we go to 1, we see all of them have 1, okay, it means that this tree here, okay, should contain, actually this tree here can contain the O's also, O, but if this tree contains the O, then this tree will become trees. So this one be O, this one might be O, and this one might be O. If like that, then everyone will be a 1. Yeah, this logic-based method doesn't really work out that well. It seems like this is a tough problem. Okay, doesn't matter. Let me just do the brute force method first. Okay, so the brute force method is very simple. So we just need to check the constraints, okay, for this is proving to be a bit tricky. I'm thinking how I can best do a, I mean, even you do a brute force, you need to check the constraints 9 times, but you need to do a count of each row and column. Yeah, because they affect each other. So let's say I do a O here, this O will add 1 to every row and 1 to every column. Yeah, so I must be very careful about where I place my O's, because the moment I place them, they will affect all the rows and columns already. So let's see. I think it still makes sense to start from the ones, then you decide whether or not to place your O there. You move on to the higher numbers, because the higher numbers definitely has more possibilities. Like over here, you see, here minimum is 2, here minimum is 2, 2, 11 by 11 will be tough already. Yeah, because of the constraints. I need to think about this, because this one has multiple constraints that you need to fill. One way I can think of solving is just basically just doing a random initialization and then just hope that it works. Yeah. Maybe let's try to solve the 3 by 3 by doing brute force first, then I think of a better method to solve the 5 by 5. Okay, so if I were to do brute force, okay, so this will be the brute force method. So the brute force will be like this. You have the fortress, okay, and then we just basically going to, okay, let's put the brute force here. Okay, so I define a method first. So over here I define check constraints, and I do a grid, and I do my constraints. Okay, for um, for row in grid, okay, so I need to do a sum of each row and sum of each column. So yeah, I can do a sum over x's like this. Oh, actually, it's quite easy to check the constraints. Yeah, I can just check whether they are equal or not. So like this. So your constraints is like that. So my constraints will be like this number here. Okay, so I just do a row and a column sum of this. Yeah, so what I can do is, because my cell count is given by numbers, right? So I can just do like row sum equals to mp dot sum. Okay, I sum over across an axis. So I sum my grid. Axis is 0. Okay, 0 will give, like, if this is 0, it will sum across the column. Actually, this is a column sum. Yeah. Yeah, so we do a row sum and a column sum. Okay, so what we're going to do is we're going to add this up. Okay, and then we reshape this to be a form minus 1 1 dot reshape 1 minus 1. So row sum will be given by like that. So actually this should be 1 minus 1. Okay, and then what I'll do is new grid equals to column sum plus row sum. Okay, so this will do like broadcasting. Yeah, so if we do broadcasting, then this should give you a nice, so this is like broadcasting. So then we just check whether it's the same as our constraints. So what we can do is we can just convert this to a string. So I mean, one way to check whether the constraints work is just to check whether they sum to 0. So maybe what we can do is we can do grid minus constraints, because all of them are like a matrix already. Okay, let's just print out the new grid. Okay, print out the constraints also. Okay, then after that we just check Okay, how do we check whether all of them are 0? So we can just do like all. Okay, all method in Python, what does it do? All method will just basically return true if all elements are true. So actually I should use the any method, okay, because I just want to check whether there's any zeros inside there. So any returns true if any of them is true. So any grid minus constraint. Yeah, I think this should work. Later we just check. So what we should do is we should just do, oh, wait a minute. Okay, so I will just do like either 0 or 1 for each of the fortress. So actually maybe doing it this method, this manner might be a little too difficult, because I need to do like 0 or 1 for each of this fortress itself. So like, yeah, maybe what I can do is like that. For so I want to find a way to convert I in range to the power of 9. So if I percent 2 to the power of I percent, let's do a size by size like that. I can do it. Then we can reshape it back like that. And we can then check the constraints. So we can then check the constraints for fortress. Okay, grid and the constraints. The constraints will be cell count. If this works, okay, then we'll just print. Then we'll, we'll just do this. Okay, this is a very lousy code. Okay, I think, okay, maybe this may not work, but let's just see the brute force method works first before I even try implementing else other stuff. So I in range to the power of 9 for j in range 9. Okay, this really just solves the 3 by 3 case. Fortress j will be like I percent 2, something like that. Yeah, be I percent 2. Okay, so no, I percent 2 to the power of j. Actually, I should just check whether or not the binary representation of this contains. So fortress j equals to, let's do a binary method. Yeah. So I want to convert this to binary. I just do like binary with fixed length. Yeah, because I need the length. Something like this. Yeah. do a bit string. Okay, and then basically the fortress j will then be equals to the bit string j. Fortress dot reshape. Okay, let's see whether like, okay, axis 1 is our bounds for array of dimension 1. Let's print the fortress here. So it seems like the fortress itself did not get reshaped. Oh, it should be reshaped by size comma size. The truth value of an array with more than one element is index 3 is out of bounds. Array of size, this is 0 with size 3. Okay, let's not do the reshape here then. Yeah, I mean, it's causing a lot of issues. Let's just optimize this code such that we, hey, yeah, this problem is proving difficult to solve. If you have ideas of how to solve, you can let me know. Yeah, I think I'll just try to solve the 3 by 3. Yeah, I'll digest it over like my sleep tonight, and I see that I can solve the 5 by 5 tomorrow. Yeah, because this problem is a hard difficulty. It's definitely gonna be difficult. I do stuff in neural networks, reinforcement learning, neural networks, supervised learning, self-supervised. Yeah, now I'm doing something related to some Yen LeCun stuff on self-supervised learning. Yeah, quite interesting. Yeah, I mean now a lot of code is online. You can just download those code and then you can run it. Yeah, one day I'll do a stream of like using deep Q networks to solve some game like maybe Wordle or something. Yeah. Yeah, definitely. Yeah, human level AI or even better AI than humans is possible already, like in certain domains like game playing, where you need consistency. Using Monte Carlo tree search, you can already search much deeper than what a human brain can search. Yeah, but if you talk about general human AI, like how we can like do various things, I think that's still in the works because it's hard to get computer to do stuff in a general sense, especially when it hasn't seen much data. Yeah, that's the difficulty of machine learning right now. So that would require some work. I believe it's because the models right now do not program enough of the like some form of models that can be generic. Like CNNs, convolutional neural networks, they are generic in terms of image patches. Right now, we just need to find the right model structure in order to encompass the world knowledge. That's my view. Yeah. You wonder if we are also robots? In some sense, yeah, I guess we are robots. We work with some form of algorithm that is fueled by our brain cells, or maybe it can be other parts of our body as well, not just the brain. Yeah. Who knows? Maybe one day we realize that we are robots as well. Yeah, and you can just like unplug yourself or something. Yeah. How do you know you're not a robot? Well, what is a robot anyway? A robot follows instructions, right? We are following some instructions that we don't really know how to decipher right now in our heads. Does that make us a robot? I don't know. We could be robots that don't understand ourselves. Yeah. Interesting discussion here. I think it is something that like we won't know for sure because like the world is so complex. Yeah, and your reality right now may not even be real, but everything is like a black box processing it. Like you can see my face now. Do you think that I'm real, or are your senses telling you a certain story? Everything is perceived through your senses. Yeah, so I mean, I wouldn't say that we like are definitely not robots. Okay, we might just have an algorithm that we don't understand that well. You see, I'm programming an algorithm right now. Okay, but you know, if we make this algorithm like super complicated, like over like hundreds or thousands of processing units. I mean, in think of computer sense, okay, but the brain may not work like that. And then you come back and agglomerate the answer together. I mean, it might look very complicated, like intelligent, like, but we are still following some instructions, right? Yeah, yep. So yeah, I hope that sort of answers the question. Okay, let me just try to solve this thing here because I need to j percent tree j. I think we do this first. Okay, so yeah, I do have a lot of outputs here, so I just need to make sure that okay, I think my fortress is ready. Okay, I'm ready like randomizing over the fortress itself. Okay, so maybe I don't have. Okay, I let me just unprint this. Let me just unprint this. Just see whether this 3 by 3 works first. So dot o. Yeah, this is like the bit binary like that, and then we just do binary across this. Yeah, this looks good actually. So we have iterated over 2 to the power of 9 possibilities with all this. So now what I want to do is I just want to see what is my like new grid versus print new grid minus constrict. Okay, print new grid first. Okay, let's just print the new grid and then we see whether this new grid works. Okay, so we look at here. So the new grid is 0, that's correct. So if the element is like this, with dot o like that, okay, my new grid should give me like a 1 1. Yeah, very good. Oh, but why is it? Oh, because I did a row sum and I did a column sum, but I didn't like, I need to subtract. I need to subtract whether or not there's a position at that grid itself. So I need to minus grid. Okay, let's try that again. Yeah, so now this is exactly what we will get here. Over here, column sum, row sum, grid. Okay. Over here, if we have this up here, we get 1 1 1. Looks working. Looks like it's working so far. Like over here, okay, we should get 1 1 1 1 1 1. Yes, correct. 2 2 2 0 1 1. Okay, I'm confident that this new grid is correct right now. So yeah, I just return grid minus constraints now. We just see whether it matches the constraints. Okay, so let's see whether like this is true or false. Oh, okay, if I were to do like that, true, true, true. Oh, it just prints true for anything. Okay, it means that if any of them is okay, so I need to like do a reverse of this, right? Okay. Now everything is false. Okay, so okay, looks good. Looks good. Okay, so what I want to do now is I just want to make sure that I can brute force and it can generate out the right fortress. Okay, so I have done all this so far. New grid, I've done the fortress. Okay, this is just for size 3 by 3. Okay, check the constraints. Let's just not print this fortress, see whether this works. Okay, so why is there this because I printed out this fortress here, which I don't need to. Okay, so apparently this is not working. So maybe what I can think of is I can do this empty.sum. Okay, absolute value of this. Okay, so basically if this absolute value of this, okay, and the sum is 0, it means that the return if the grid matches the constraints. Yeah, so I just doing this. I see whether this works. Oh, oh, it didn't work. Okay, so apparently it should be like this. So we just need to see whether like we generate that pattern out. So maybe what I can do is like this. Let me just print this out. Oops. Print this thing out to just see whether I have worked correct. Use the right tools. Okay, I also want to print out like my new grid. Okay, just to make sure that print new grid and print the constraints out so that you can see whether it works. So the new grid is this one and the constraint is this one, so the sum is 15. Okay, so if let's say my new grid and the constraints are the same, I should have it print out equals to 0. So new grid equals to constraints. So indeed, if my new grid is constraints, my because I did grid minus constraints, no wonder. Okay, so I think this should work now. There should be a 0 somewhere. So let's see. All right. Hi Murat. Yeah, I saw that you solved this problem. Okay, I don't know how you did it. Oh, my brute force method is working for the 3x3. Oh, I don't think this can scale for the 5x5. Yeah, but it's working for the 3x3 at least. Yeah, of course, quantum computing will get big. Okay, why do I say so? If you can compute exponential time problem in linear time, you can do a lot of things. I can solve this problem using quantum programming with brute force. Imagine that. Yeah. What are the applications? You can do a lot of parallel processing, a lot of computation with very little processing power just by using the qubits themselves to store quantum states. Yeah. With quantum programming, a lot of programming problems right now will be as easy as printing hello world. Yeah, that's a bit of an oversimplification here, but you get the idea. A lot of things that we can do right now that are considered difficult, like the cryptography. There's this RSA cryptography. Yeah, now they use a modulo of like a very big number in order to do like public codes. With quantum programming, quantum compute, you can actually crack that code like within seconds, which will mean that we need a more stable code. So people are worried about that right now. I mean, we haven't even invented quantum computers, and people are already thinking of all these possible outcomes. So if you ask me, there's a legitimate worry for quantum computing. Okay, but I would say that it's actually more beneficial than worrying. Yeah, have you heard of alpha code? I've been recently doing alpha code like stuff. Yeah, they actually essentially just take the entire database of whatever people have done. Like this is the input to the problem. The input is whatever you see here, whatever you see here. It's very similar to what CodinGame gives you. Okay, and the output is the program. So the output will be like this. So yeah, they actually learn a lot from like human programmers and in like top coder competitions and stuff like that. I can't remember what was the competition they took part in. It's not CodinGame, it is Code Forces, yeah. So then it using this mega transformer network. Let me just show you transformer network image. Okay, so I wonder if we can see. Yeah, so using a super mega transformer, I mean they use BERT kind of mass encoding, but using like some form of architecture like this, you input and output embed, and then like you Yeah, you basically try to focus the right attention on particular phrases, and then you can generate like a program based on like you can tell it like what is the, let me see whether I can show you. You can tell it what's the rating of uh, the difficulty of the problem. So a more difficult problem, maybe you have a longer code. You can tell it like what kind of program structure it is. You want C++ or Python, and then whether you want correct or not. So actually, it's quite cool because like they use this, and then they can actually get a lot of the information from previous problems to try to solve a new one. And like I think it's pretty cool. Yeah, I just think that uh, I don't think this is how intelligence is derived. Actually, this is like how do I put it? It's probably just a way to like do pattern matching of whatever known patterns. But if you ask it to solve a problem that people haven't seen before, I don't think it can solve it. Yeah, but I mean it's pretty cool that this even works to generate a proper program. Yeah, because it's not easy. I mean, like a program like this, we can actually get it to like fail in multiple ways. In so many ways, a program can fail, and if you want it to work, that's really difficult. Yeah, right. So I really think this is something that's interesting. Yeah. Okay, so let's see. No, we won't be useless. Don't worry about it. Okay. I've shown you in this stream that a pure brute force method can only solve the three by three. Look at that. Yeah, if I do a five by five, if I do a five by five, it times out. So it means that for five by five, a more efficient algorithm will be needed. Okay. And I think there's one way to do it is to just start from the lowest numbers. Like instead of filling up the string from like instead of filling up the string from, so basically we need to find a way to terminate. Okay, the moment we realize that we have bust the minimum sum of any of the rows or columns, we should terminate that evaluation. Yeah, and perhaps we can even use the information of the minimum. Like over here you have the minimum number is 2. Okay, you can use the minimum to like decide or not whether or not like this row has a lot of circles or not. Yeah, so if like this minimum is 2 and then this one the minimum is 5, it probably means most of the O's are at the top. Yeah, and very few of the O's are at the bottom. So we can probably like start work by filling up the rows with higher number first, followed by the lower numbers at the end, because the lower numbers probably don't contain anything. So you can start by filling up at the top first. Yeah, so I think that's one way to solve this problem is to in terms of search processes, what this does is that it prioritizes your search to areas where you pay more attention to. I guess something like attention model. Yeah, I mean, in this case, I'm artificially telling it to pay attention to areas that have a higher chance of being filled up or higher chance of being a O. Like you look at these numbers with like 7. I mean, this probably means that they have a O anyway, right? You see, a 7 here probably means that they are filled. Okay, let's take a look here. A 3, a highest number probably means that they are filled, right? Because if they are the highest numbers, they probably have something. I mean, if you look at the 5 by 5, the highest number 7 here has an O here. So you can save some compute time here. Like over here, the highest numbers, I guess is a D. I guess it's a D. So a higher number D has something here as well. So yeah, I mean, one way to do this also is because like we already know, like based on the row and the sum of these columns, we already know how many pieces are there. I mean, okay, let's challenge you. Okay, if given the row counts and the column counts of a grid, Okay, row counts means like the number of things present in each row, and column counts means the number of things present in each column. How can we tell the number of like O's there are? Okay, that's a very simple way to do it. Okay, yeah, I think Murat knows because Murat solved this problem. Yeah, so we can actually tell the total number of O's present in the solution just by the row counts and the column counts. Then we can reduce this problem size from 2 to the power of the number of positions. In this case, like 11 by 11 is 2 to the power of 1 to 1. We can reduce from 2 to the power of 1 to 1 to just simply picking a combinatorics problem to picking like X number of O's out of a given sum of blanks. Yeah, so we can reduce the problem scope just by doing that. And let's try to do it. We try to make it more efficient. Okay, iteration two, efficient brute force method. Earlier on it was brute force, right? Now it's efficient brute force. Efficient brute force. Okay, so I want to basically find out, okay, the row and column counts. So like, let's just copy this thing here. Okay. Okay. Here we do num counts. Oh, we do cell count. Okay, so very simple. Based on the cell counts, okay, I will then basically do a form of map. Okay, so the mapping part we'll do later. So, hey, yeah, see you, Murat. If I cannot solve this problem, I'll ask you next time when you come on the stream. Yeah. Oh man, this problem is harder than it looks. I thought it was quite simple, but once I do it, I realize I face the curse of dimensionality. Yeah, that's you, Murat. Okay, let's try to solve the 5 by 5. Okay, I think I can solve the 5 by 5 live on stream. I don't think I can solve the 11 by 11. Uh, we need a lot more optimizations to solve that. The 31 by 31 is like it's almost impossible. I mean, using this kind of method, there must be some trick to do the 31 by 31. Yeah, but at least the 5 by 5, I'm confident that I can code a more efficient method to solve the 5 by 5. Also, like a brute force method, but you terminate the searches early for parts that doesn't work. Okay, so let's try this efficient brute force method. Okay, so we find the column sum and the row sum. Okay, so the way to find out the total pieces will then be you take the, okay, so actually we need to actually like when we sum this cell count, these are all the rows and these are all the column, right? So yeah, so when we get this cell count, actually um, when we get the row and the column sum, the row sum will be, no, we cannot do on the cell count. So just given the cell count itself, how do I tell, okay, what are the number of counts? Actually, I think it's very simple. So you see every O over here will impact a +1 to every single cell on the row and every single cell on the column. So this will be size plus size minus 1 because there's only like 2 over here. So size minus 1. So I can just take the sum of the entire cell count. Okay. Okay, and then I just divide by size times 2 minus 1. Okay, let me just print out total pieces just to make sure that this concurs with what I know works. So this is 3, so there's 3 total pieces for this, and there's 3 total pieces for this, and 5 by 5, there's, okay, let's ignore the bottom part. Oh, 13, okay, 13. So is the answer 13 pieces as well? So for the 5 by 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 13. So very good. I figured the algorithm to find out the total pieces that we have here. So okay, based on the total pieces here, okay, I already know find out total pieces present. Okay, and then just do random permutation of these pieces. Okay, so now we can do the, so now we have found out the total number of pieces that, I keep pressing Control S, but okay, now we find the total number of pieces that are present on the grid itself. We can then figure out like how we can do a permutation of these pieces, okay, such that we represent this output here. So now I already have the total number of pieces, I have the total cell size, I can do a permutation. So we can do a permutation in Python. So Python have this permutations thing as well. Yeah. Or actually combination. I don't need to permute. Okay, I can just do a combinations. From iter2 import combinations, and then oh no. Okay, so uh, okay, maybe I don't take gig from gigs. I will use iter2's library to just see how to do combinations. So in Clash of Code, actually this combinations thing is it's quite useful also. So you can do here, combination is like this. You return R length subsequence of elements from the input iterable. So this iterable can be like O and dot. And then we come up with like 2 means like A, B, A, C. Okay, so this is not exactly what we want. Okay, we want to basically do some variation of, or like do some okay, maybe the right thing should be permutations. Like given a certain array, okay, all possible orderings of the iterable. So it's like this A, B, C, D. Then if I do like 4, I will, like over here, range 3, I will get all possible orderings of this 0, 1, 2, 0, 2, 1. But I don't really need all possible like this, because like, okay, imagine if I do 0, 1, unique based on their position. I want it to be unique based on the value actually. So if I have a certain range, and then okay, I think I have to use combinations. So let's try this. Okay, I use combinations. Okay, so for each in, okay, combinations. Okay, and then I will do, okay, let's just try to print out the combinations first. Okay, so each of these combinations, let's say O, right, 0, 1, 5. Okay, maybe I don't use this. I use a like O dot dot O dot dot O. Okay, how about permutations? Okay, so it prints out all of this here. There's still a lot. I think permutations is the right thing to use. But you see, permutation, it sort of doesn't cater for like cases whereby there's repeats. No, it's not the questions today are harder. Oh, you mean for the Clash of Code? Yeah, maybe. If you're talking about this hidden fortress, it is rated hard. So I think it's really hard. Yeah, I mean, I solved the 3 by 3 already, but to solve the 5 by 5, I think my limit is probably the 5 by 5. After that, I probably need to look at like ways to do like depth first search to like try to search through the space in a more efficient manner. I wonder if like I can use I just Monte Carlo and just do a random search and then hopefully it just pops up with the answer. Actually, evolution based algorithms might work for this. Like you just try to find things that are like fit, like very close to the fitness value, and then fitness value being the constraint satisfaction value, and then you just like, randomly permute. That might work actually. Actually, kind of think of it. Evolution based algorithms like genetic algorithms might work for this problem. Yeah, why not? Yeah, I don't mind coding a genetic algorithm to solve this. Yeah, but let me try to solve it by pure logic first before I go to like evolutionary algorithms because evolutionary algorithms have some form of randomness in it. I think this problem can be solved using deterministic methods. I really think it can. But first I need to find a way to like do some permutation. So what I can think of is okay, like this. Okay, maybe we don't need to do the permutation. We can just do this. Okay. Uh if bit string dot count 0 or dot count 1, okay, not equals to total pieces, continue. Yeah, we can just do this. This should be able to like filter out more of the state space because we take into account like whether or not we have met that particular constraint, which is like have we gotten everything in the total pieces. Okay, it seems like we still cannot do this method. Okay, because 2 to the power of 25 is still too large to iterate over. Okay, it's still too large to iterate over. Okay, we need to find a way to plant this ones into the grid. Okay, and change the position of the ones accordingly. Okay, we need to find a way to plant this ones in. So I think one way to do it is just to plant the number of like these total pieces, and then we just like change the piece of a one and a non-one. We change the piece such that it will satisfy the constraint better. Like we can do like a brute force algorithm to do that. We just find for each uh, one, okay, that we place in there, like whether or not it can be better placed in a separate position. Okay, if it can be placed in a separate position better, then we go ahead and do it. Okay, and we can look at maybe placing the ones at the places where the row and column interactions, or basically you see over here. I may have an idea how to solve it. So you go by all this like tools over here. Like if you see a 2 here or the lowest number, it means that probably there's no O here, right? So it probably means that we should place the O's at the highest numbers first, like 7, 6, 5, 6, like that. So after we place it here, if there's any clash, okay, we should take and place them at the lower values. Yeah, but essentially the higher values should get all the positions first. Then we just take and randomly displace. Actually, this sounds a lot like genetic algo, right? Yeah. I think I can solve this with genetic algo. I just don't think I have time to code it out right now. Maybe tomorrow. Yeah. But let's try to think of this as I already have the total number of pieces I can place in the grid. I already have the total number of pieces, like rows and columns like this. I just need to find out how to place them. It's like I have all the pieces now and I just want to find out how I can place them on the grid. I have all the pieces, I want to place them on the grid. All the pieces. Okay, let's try to figure out a brute force method to do the combinations problem first. So how to get number of ways to position. Mm, I thought combinations could do the trick actually. Yeah, like if you take combinations out of this. Ah, yes, we can use combinations to do it. this will be the total grid size, and this will be the number of pieces. Then we just plug them out. Okay, so let's do it. So each in combinations. Okay, so this one will be range size times size. Okay, and then what we will do is we will do like total pieces, print each. Okay, let's just try to print this out, see whether this works. Combination. Yeah. Okay, so that's how we do the combination. Okay, combinations, combinations. Integer argument expected got floats. Okay, this one should be a divide. Okay, so these are the positions where we place it. Okay, so for each in this, okay, so we already know that each is like that. So we don't need a bit string anymore. Okay, so for I equals to to 0 or 1 if each. Okay, so actually what we can do is we can just make this we can do it here. We can make the fortress is a empty dot zeros like that. Okay, and then for okay, so this is like pieces for each in pieces. Okay, because each is this number here. Okay, fortress each equals to 1. Yeah, because then the rest will be 0 already. Okay, let's see whether this works for the 3 by 3 now. Index 3 is out of bounds for um, yeah, like this. Yes, okay, so it works for the 3 by 3. Will this work for the 5 by 5? Oh man, it still didn't work for the 5 by 5. So just naively doing this is not the solution to do that. Maybe I should sort it. Maybe I should sort my combinations that I get. Yeah, so I have this. Okay, something's wrong here. So I want to do a sorted list of my combinations. Okay, so what I can do is I can sort them. I can sort this out by yeah, I could just sum my combinations with like this list of combinations here. I could sum by the cell count I. P equals to lambda x. For each of this, I sum by the total number of cells here. So if over here is 2 and over here is 3 and over here is 2, I should prioritize those solutions first rather than those with zeros and ones. Okay, let's see whether this like sort of works. Okay, so it prints out like over here for this case here. It prints out 358. What's 358? 0, 1, 2, 3 is this one. 3, 5, 8. 3, 2, 1. 0. Where's my 0? 0, 1, 2, 3, 5. Yeah, it does seem to sort out in increasing order. Then here's 1, 2, 3, 4, 5, 1, 6, 7. Yeah, it looks like it's is being sorted. Yeah, but it still didn't seem to solve the 5 by 5. I mean, now there's no timeout error, which is great, I guess. Uh, why is there no pieces printed out? I mean, I should print out this. It should print out pieces. For some reason, it didn't print it out. I see another 3 by 3 prints out my pieces here. But for 5 by 5, it didn't. So there must be something wrong with this thing here. Yeah, maybe if I take away this part here, I take away the key. Somehow it doesn't print out at all. Yeah, somehow it doesn't print this out, which is weird. Which is weird. Maybe this one doesn't work. Oops. Maybe this one doesn't work. So I should get the whole list here. Oh no. Why is this not working? How about this 5 by 5? Yeah, somehow it doesn't seem to print out my random permutation of my pieces. I mean, the 3 by 3 is solved already, but the 5 by 5, why? Why is it not printing out? It should print out this. Hmm. I think it might be too big to put in a list in a 5 by 5 because there's too many combinations for that. We might need to define our own generator to do this um, position printing, but it seemed to work well for the 3 by 3 because if we do like 3 by 3, it actually works for the first two. So the 3 by 3 and the another 3 by 3 here, it works. Okay, just that for the 5 by 5, I think this method doesn't work because it fails to print out the list. The amount of combinations here is too great and the program just collapses. Okay, so we need to find out a way to. I think this method works actually. This heuristic works. So basically, we search and we put in the O's at the positions with the highest number first. So yeah, maybe what I can do is I can sort the index. Okay, the index of this. Okay, with the number, and then I can then like proceed to like map based on the index. So okay, let's see how I can do this. Uh, okay, I need to find a way to like to generate my number of combinations based on like a certain inherent factor. To I need to do my own U like this. Okay, so I will define my own enumerable. I will define my own define generate pieces. Okay, and then there's a iterable here. So the iterable is basically I need to do my own combinatrix function, okay, in order to solve this problem, because this is not easy, you see. Yeah, I mean, my method works for the 3 by 3, but it failed at the 5 by 5. So I need to find a way to like generate the pieces, okay, such that I will prioritize, okay, the pieces that have the highest uh I prioritize the pieces with the highest number of cell counts first, and I put the O there. I see whether it works. Okay, so let's try to solve it. Okay, actually a Monte Carlo method might work for this, but let's just try to solve this first. I might need to code this in C++ also, because I think Python might be too slow to do the 31 by 31 later on. But this is just a concept. I wish Python was as fast as C++, because I really like coding in Python better than C++. C++ is very lengthy. There's a lot of stuff that you need to do in order to make your code work. Yeah, Python is so much easier. Okay, so let's do the code for generate pieces. And generate pieces, we put a seed over here. Okay, so based on this seed, we then generate the pieces we need. Okay, so what is this seed? Okay, so maybe what I can do first is I can do some form of mapping to map my index to the numbers here. So this will be over here, numCount.index. Okay, for I in range size. Okay, so we get a cell count already. So what we can do is for my list, I call it my list. Okay, my list dot append. Okay, for number in cell count. Or actually, what we can do is for j in range size. Okay, so my list dot append. Okay, we append the cell count ij, which is the list here, and then we do I times size plus j, which is the index. So we can then sort by cell count and index. So print sorted my list. So if we print the sorted of my list, we should get the expected indented block. Oh, okay. I think maybe I shouldn't like destroy this first. Let's just do like for pieces in this first. Okay, so that we can keep this. So 0711. So this is my index 0. Okay, cell count ij is 0. Okay, cell count is 1 1. Okay, let's just print my list first without the sorted. So 2 0 1 1 2 2. Okay, so if I do my sorted of my list right now, okay, I'll get 0 7 1 1. Okay, so it's sorted in the wrong order, so we need to do like reverse equals to true, and this should give me like 3 3 2 6 2 5 2 4. Okay, so basically I want to put my pieces in the first 5 here. Okay, so this will be my indexes that I don't need the I don't need the first number, I just need the second number here. So what I can do is, okay, I can do like this. Okay, so this is a shortcut. So index map equals to, Okay, so this is my uh, y0, y1 for y in this. So my index map will tell me what are the focus cells first. So I should focus on my 3 first. 3, 4, 5. Then I focus on my 6. Then I focus on my 5. Then 4. Then 2. Then 0. And 8. Then 1. Then 7. Yeah, so this tells me what cell to focus on first to place my piece there. So I then need to brute force over this. I just need to keep placing the thing, okay, inside based on my index map. So now we got the index map. We can then proceed to modify this function to place my pieces, because I got my total pieces now, to place my pieces into this map. Okay, before we go on, let me just make sure that my 3 by 3 is working first. Okay, it's working. This 5 by 5 is a pain in the ass. Yeah. Okay, I mean, I thought I just did a simple like efficient brute force. I can solve by 5 by 5, but no, I can't do an efficient brute force and solve 5 by 5. It still didn't work. Yeah, it's so annoying. Yeah, I have to do something more. Yeah, I like this kind of puzzle actually. Like it really trains you to think out of the box, because the in the box solution will definitely not work. That's why it's a hard puzzle. If it can work, then yeah, yeah. I mean, this puzzle is really hard. Yeah. Anyone here solve it? Anyone here solve it? You want to share your opinions of how to solve this puzzle? This puzzle can be found. Let me just show you how you find it. You can just go to I think it's under events, and then you can go to here, the puzzle, the hidden fortress, and then you can solve it like that. Yeah, Donald Knuth likes to say stuff like that. I don't think so. I don't think P equals to MP. I mean, if P equals to MP, why hasn't anyone found the relation yet? True. I mean, if you slice up the exponential, you will get polynomial. Yeah, you get many branches of polynomial. But if you have like polynomial, many branches of polynomial, then that will be exponential. Yeah, so I guess it's how you view the problem. If you view it as many sub problems with a smaller complexity, but you have many such sub problems, you might still get a very high complexity. I don't know. Yeah, no one has proven it. No one has proven it right. Uh, no one has proven it wrong. Yeah, but my gut feel is that it's probably not. Yeah. There can be what infinite algorithms to solve the same problem. What's infinite? You mean infinite algorithms to solve? Well, of course. Yeah. I mean, your algorithm might just add one and minus one to your variable. Like for example, if I want to find an algorithm to solve the sum of all numbers in an array. Okay, the straightforward method to do it is to just sum up all the numbers in the array. But if I do a sum of the numbers, I plus one, then I minus one. That's also another algorithm. Plus two, then minus two. I mean, you can have redundancies in the algorithm, and it will still work. And you can count that as a separate algorithm. So whatever he says is definitely valid. Yeah, but with infinite algorithms, does that mean that you can prove one is p equals np? That may not be the case. Yeah, showing that there can be infinite algorithms does not equate to solving p equals np. I mean, I wish it was that simple. Yeah, because then you can get like maybe the Nobel Prize for solving it. I don't think anyone has solved it. Yeah, if you have solved it, feel free to write your paper and get the Nobel Prize. All right. Yeah. N equals to one done. Sorry, what do you mean by n equals to one done? Coffee cat. You mean this one? 3 by 3? Yeah, 3 by 3 is solved. Yeah, but this 5 by 5 is the problem. Okay, let's not get distracted. I want to solve 5 by 5 if possible. So I figured out a way to view this problem differently. So my 3 by 3 solution was very simple. It's essentially just brute forcing either a 0 or 1 value for each cell, and then just checking whether this constraint is met. So that has solved the 3 by 3. Okay, but for the 5 by 5, I figured out how to get the total number of pieces, which is just taking each of the row counts, each of the column counts. Okay, basically I just divided by size times 2 minus 1, which is like the number of times each piece will affect the row and column. Yeah. So yeah, now I need to find out how to like put this in the index map. Okay, so I have an index map now. I need to parameterize it. So like I want to put my pieces in like one in the first few, then I move to the next one, then move to the next one. So is there a way to do this? 1 1 1 1 0 0 0. So if I start like that, I will then shift my this piece down to like that, then shift this down to like that, shift this down to like that, and so on. Yeah, I will need to find a way to shift these pieces such that, yeah, I can start by placing the pieces in the most I mean that might amount to like some form of binary addition. I can shift my piece down one by one. So what I want to do is I want to shift this here, then the next one will be like that, next one will be like that. Is there a way to do this? Then after that I do like that. Hmm. Any tips on how to do an iterator like that? I think there might be something to do with binary. Like I can get the next binary number with three. Let me just search. Oh no, I got locked out. Binary representation of the next greater number with same number of ones. Yeah, that's what I want to get. We can iterate over all the numbers from 2 to the power of x. I tried that. I tried that. It timed out. 2 to the power of 25 is too big to to iterate over. Yeah, because for 25 squares, you need to loop through 25 times. So like 2 to the power of 25 is, it led to a timeout. This is what happened. It led to a timeout. Yeah, so I need to find a way to do this. Can you believe it? I can't even solve the 5 by 5. What is this? They gave me so much, 3 by 3, 5 by 5, 11 by 11, 16 by 16, and I can't solve the 5 by 5. So irritating. It's like telling you, you suck. You can't solve the 5 by 5. But that's not the right attitude to have. It means that the solution is yet to be found. The solution is waiting for us somewhere. It's waiting for us somewhere. Yeah, we need to just find that solution. Okay, let me try. Let me try to think of how to solve this. Yeah, so next greater element of same set of bits. This is not the way to do it. Yeah, this is like, it's not the way to do it. Yeah. Mm, I don't know. I mean, I can think of one way is I just take the most significant bit, and then I just shift it down by one. Okay, and then after that, so I can do a if method. So after that, if my one has put over here, I can then shift the second next bit to one. No, I'm just trying to find out a way, okay, to like return a set of mappings, and this set of mappings will mean like whether or not we put an O in that position. So like initially we put like O's here. I've already set my index map to map the highest number first. So we put the O's at the highest number first. So like that. So I need an iterator that given this, okay, I output the next string with my ones, okay, shifted by one. Okay, then if like let's say one is over here at the back, I then need to find out the next possible one, okay, that is away from this one. So like the next possible one here, and then I need to shift it down like that. Yeah. So essentially, it is essentially what I'm trying to do is I'm trying to do a bit shift of the next most significant one downwards. Yeah, and I mean it can be actually easily done with multiple for loops. Yeah, I can do like multiple for loops to like parameterize this. Mm, I'm just thinking whether or not I can find an easier solution. Yeah, I can try to solve this. This is called the hidden fortress. It started off easy. It started off easy because like I thought it was an easy problem. Okay, I mean, no, I didn't think it was easy. I knew it was hard. Yeah, so you see you have this like O's over here. So like each O, each row and column will give you a sum. So like this particular piece here, row and column, you sum up, you get two O's, right? So it's two. This one here, you only sum up the row here, which is this one here, and there's nothing in the column, so it's one. So given this state of row and column sums of your O's, your aim is to output O. Yeah, combinations of ether tools didn't work. Okay, why didn't it work? Because there's too many combinations to print out. So I can't do this method with ether tools. Yeah, I mean I tried. You see, this is the combinations method. Yeah, so if we actually maybe we can do a generator method. Actually, let's try this. Wow. Okay, so maybe we call this generator. Yeah, actually, good idea. We can try using this. Wow, generator. Yeah, let's try to solve the 3 by 3 with this. Pieces is not defined. Okay, let's try to get this. Okay, it works like that. All right, so now I have my index map. Actually, that's a good idea. I can just put the index map to the iterator like that. I don't have to implement this myself. So, okay, I guess what this does is that maybe I print out the pieces here so that we can take a closer look at what it prints out. So 0, 1, 2, 0, 1, 3, 0, 1, 4. Actually, this exactly is what I wanted to do. I wonder if this works for 5 by 5. Oh, 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 actually, this is what I want. Thank you for the suggestion. This is what I want to do. This is exactly what I want to do. The combinations for ether tools has done a great job of doing this. Yeah, have done a great job. I mean, they have done basically what I wanted to do. Like, yeah, okay. But one thing I need to do now is I need to, instead of putting it like for each in pieces, right? So what I do is a map. We map it. So we do like mapping size and mapping. Okay, let's try this. Okay, let's not print the pieces now. Let's just do this 3 by 3, 3 by 3. Please work, please work. If not, I have to do genetic algorithms already because, oh else. Even this optimization didn't work. So my optimization was I placed the piece at where this number is the highest. Okay, and then I just basically just change the mapping. Okay, such that the mm, okay. So let's think about it. If, let's say there's like 50 pieces. Okay, and if I evaluate like so, okay, this is the so this method didn't work. Okay, yeah. 5 by 5, the total pieces is 25. Yeah, but it'll be very easy if it's just 25 because like I mean, okay, let me just do a custom. Okay, let's do a 5 by 5, and then maybe what we'll do is we'll do only the top row will have it. So like this. Yeah, this method, I think my solution would be able to solve it, because you see, this method, my solution would solve it because it's able to map the highest numbers. Like if I put another O over here, okay, then this whole row will be 2, okay, and then this one will be a 6, okay, and then this one will be 2 also. Oh, actually this is like a layer cake formulation. See, every time I put an O, right, then the whole row and the whole sum will add up by 1. I think I solved this problem already. Yeah. Hey, see you, I asked Quebec. I think I solved this problem already. The problem involves reducing the number of ones like this. So you see, if we realize that this is like a layer cake formation, okay, so I can essentially solve this backwards. Actually, a lot of problems you solve by backwards actually works quite well. So you see over here, if this is like a layer cake, when I put this O over here, I need to add 1 to every single square here. And I add 1 to every single square in my column. Oh, Salah. This one, yeah, is correct. Yeah, so what I can do is I can see which row, okay, and which column, okay, can enable me to minus 1. So like over here, if I were to take out from this 1 itself, okay, I will not be able to, no, I need to basically find out the row and the column sum of the highest piece. So like this highest piece here, I need to make sure that this entire row here, because going by the layer cake analogy, we need to make sure that the total sum over here in the row and the total sum in the column, okay, must be the highest. Okay, then we can proceed to take out one piece. Yeah. Yeah, thanks Omniscient, but I think the problem is no longer about combinations, because solving it by the combinations way will fail. There's just too many combinations, even if you take n minus r. Yeah, so there must be a more efficient way to do this. Yeah, I think the layer cake method works. Okay, so the layer cake method, let me just describe. Can you see my screen down? So the layer cake method is like this. You you look at the, because you see every time I add an O in this, I have to add every row here by 1 and every column here by 1. Okay, what this naturally means is that if you have a piece at a particular position, okay, going by the layer cake analogy, what I should do is I should add 1 to every row and every column. That will be a total number of ones added by a size times 2 minus 1. So you have to add the entire row and column summation of your numbers will be added by size times 2 minus 1. Okay, and going by that analogy also means that if your particular number of that grid has the highest row and column counts, okay, and we currently haven't put the O there yet, we definitely have to put the O there, because going by this logic, we will need to accord the highest sum and of the row and the column counts of this particular cell. Okay, we need to accord that by the, how do I put it? The row and the column sum of that cell which is the highest, okay, should be the highest lah. I mean, because it should have a piece there. Because any other piece away from the layer cake that you don't add in there, if you let's say put the piece here, but you just look at this tree here, the row and the column sum here shouldn't be as high as the row and the column. Okay, let's just count it out. Okay, 6 plus 2 plus 2 plus, okay, this a bit, Yeah, correct. You do a greedy solution to pluck out the O's each time you see this. Usually you do backwards engineering. You do backwards engineering. You just pluck out where the O is based on reverse engineering. Yeah, I'm just seeing whether this might fail for any test case, but let's see the 3 by 3 test case. So going by this layer cake approach, you see 2 3 2 3 2 2. This is definitely the highest. Okay, let me just copy and paste this one. Copy. And this one's supposed to be 0 dot 0 dot 0. Okay, so going by the layer cake approach, I will find the row and column sum here with the highest. So this one will be a O. So I can take this O out, plug it into the grid. I minus 1 from each of these numbers here. Okay, then now we have this. Okay, 1 1 2 1 1 1 2 1. Okay, so we have this instance, okay, where okay, we can have two possible solutions. Okay, one solution is because we already take out the O there. One solution is this over here. Okay, 2 1 1 1 1. No, actually, this is either this or this because this have the highest row and column sum. So I take away this over here. Okay, in fact, I may not even need to save the state. This might already be the answer already. I subtract away from each row and column the ones. So now then I find out the based on the layer cake approach again, which square has the highest row and column sums. Then in this case is this square. So I have to accord this thing with the 0. So by doing a reverse construction of this, I can essentially have already deconstruct the entire layer cake like this, and I find out where exactly is my obstacle. I think I've solved the problem. Yeah, the problem is not a brute force or after it's just a basic greedy selection each step. Okay, let's try to implement it. Okay, I mean I'm not sure whether it works, but it does have some promise, right? Okay, so let's see. So I don't even need the total pieces. I mean, I don't need to know this. I can just I don't need the index map. Okay, let me just remove everything that I've done so far. Okay, I mean if I want it, I can just code it back again. So it may not be that hard a problem after all. It might just be a very simple problem disguised as a hard problem. Ah, wow, my mind is blown after I realized this. Okay, let's try to do this. Okay, so wow, some iteratively remove row and column sums of the highest element, and then update my update my update what where's my update my fortress accordingly. Okay, so I'm just gonna delete whatever I did earlier. Okay, because I think that method was hopeless. Okay, so we have a fortress like this. Okay, blah 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 blah. Okay, so like this, while some cell oops, while some cell count greater than okay, so this basically like just do layer cake approach. I call it layer cake to greedy select the position of each fortress. Okay, so like this. Okay, so we have a cell count here. Okay, we take all the row and all the column. Okay, we take all the rows and all the columns, and yeah, we basically sum. Okay, so what we do is new count equals to yeah new count equals np dot zero size. Okay, d type equals to in 32. Okay, we just call it new count. Okay, so what we want to do is I want to take each of the rows and each of the columns. So actually I can use something like this, and then I sum up like that. Actually, maybe I don't need this new count at all. I can just use this exact same thing. cell count, cell count. Okay, so I just take the row count, cell count, and then over here I minus the cell count itself. So get the total sum for each grid position. Okay, so then what I want to do is I want to find the max. Yeah, NumPy is better because NumPy uses C++ as a wrapper, so it essentially it has C++ performance in Python syntax. So if you want to do like stuff like AI bot coding in CodinGame, it's better to use NumPy. By experience, NumPy works faster. It takes a longer time to initialize because you need to do more steps than just creating a list in the backend. But after you have created that, the matrix multiplication and everything is as fast as C++. So yeah, use NumPy if you need to do array multiplications and array operations, matrix operations basically. Okay, let's see, get the total sum for each grid position. New grid equals to column. Okay, so this will be our new grid, and then we just want to um, dot reshape 1 minus 1, or actually dot reshape minus 1 will do. So this will make it. Okay, let's just print out new grid. Okay, so it means that over here I will have figured out that this is the highest. Okay, let's just see whether this works. like like over here the highest, yeah. So over here all these three are the highest, means this three should be removed. Okay, so I will then need to get the total sum. Okay, then get the up max. How do I use this? np.argmax, is it? Actually, I don't need to reshape if I use np.argmax. Let's just see whether this works. So this is a 3, 0. Okay, I think I still need to reshape. 3, 0, 2, 1, 1, 3. Okay, yeah. So we find the position with the highest up max, highest sum. Okay, after that, proceed to remove from that row and column a count of 1. So row equals to new grid. Okay, the row will be given by this new grid percent size. Okay, so what we can do is cell counts. Okay, row minus equals 1. Okay, cell counts column minus equals to 1. Okay, and then we of course need to do cell count row column because we don't want to double subtract. And then add this position into the final solution. So what we need to do is fortress row column equals to 1. Okay, let's try this. Uh-oh. Apparently this layer cake approach doesn't work all the time. I think I need to find out, like other than the up max, the fortress row column here, okay, we need to do a multiplication, okay. Times 1 minus fortress dot reshape, 1 minus fortress dot reshape. Okay, because we want to actually sort of like make sure that that particular piece hasn't been chosen before. So by doing this, if the piece has been chosen before, okay, then this will be 0. Okay, so let's try this again. Can you see that? I solved the 5 by 5. Yes! Okay, let's see whether it works for the 11 by 11 first. Oh no, it doesn't work. I mean, is my output that different from the solution? Oh. At least I got the pieces correct. 1, 2, 3, 1, 2, 3. Actually, it looks like almost the same, right, as the solution, just that there's some parts that are different. Oh, I know why it didn't work already. Okay, because we also need to make sure that the cell count for the row and the column, okay, must be, yeah, we must make sure that this new grid itself, okay, whatever that we come up with over here, we must make sure that the column sum and the row sum are greater than 0. Then we can subtract from there. If not, we cannot do it. Yeah, we have to make sure that the row sum and the column sum must be greater than 0 for that particular stuff that we are doing. So let's see, how do I do it? So we have this column sum, right? So uh, possible equals to row sum greater 0 plus, okay, let's just, yeah, let's do this row sum greater 0 plus column sum greater than. So basically only when that particular row and column can be taken out. So this will be like true plus, if I do a times, it may not work because there might be matrix multiplication. What I can do is, if let's say any of the column sum or row sum is 0, okay, so maybe I do like that. mp dot zeros, okay, size, okay, d type equals to int32. Okay, if any of columns are 0, then cannot subtract. So I mean, this is no choice. It's okay. Possible. If any of the columns are 0, I mean, there can be a way to optimize this, but I don't think this is needed to solve the problem. If any of the columns or rows are zeros, then we cannot subtract them. Okay, then we cannot subtract. Yeah, if any of the columns, let me just put this here. If any of the columns or rows are zeros, you cannot subtract. Okay, and the possible will be, so over here I need to also times possible. Okay, let's try again. Okay, so this is wrong. Column sum I, this should be row sum I and oh sorry, column sum row sum I and column sum j. Okay. Line 44. Mm, okay, actually very simple. We don't need to do this. Okay, we can just over here times 1 plus quarters. So we can just add a very big number times minus 1000 times column sum minus 1000 times row sum. Okay, which means that if this is if this is 0, then that part will be minus 1000. Cannot be broadcast. Okay, then we the whole thing, then we reshape this. Hmm, what's my fortress here? Okay, then I think over here I need to reshape this to need to put this here then minus 1000 minus 1000. Okay, times 1 minus fortress. Okay, that's a little too many brackets. Let's take away one. Column sum. So this part here will just tell us the whether it's possible or not. Okay, if let's say any of the column sum or row sum is 0, it will be given a very large negative. Okay, and let's see whether this works for 3 by 3. Okay. Oh no, this didn't work for the 11 by 11. Why? I mean, it looks like it should work. Mm, there should be a true somewhere. Yeah. Hmm. There's no true at all. This row sum and column sum are not. No, I'm not trying to solve the equation. I'm using the layer cake approach. I'm just solving by putting the square that has the highest intersection of the row and column sums, okay, as my thing that I want to take out. Then I place the put there, okay. I place the place the I place the piece there at the position where it intersects the highest row and column sums. Okay, I'm just doing an iterative approach, okay. But I need to make sure that I don't subtract to zero. I mean, I don't subtract a zero and then, oh, I know why. It's not the row sum that I want to find out. I just want to find out whether the row sum, okay, is greater. Okay, it needs to be greater than the size, okay, so that we can subtract. Actually, should I do this? No, actually, what I should do is I should sum this one. Can remove row equals to np dot sum, okay, cell count. Yeah, I used the wrong metric. Should do something like can remove row and can remove column, okay, and then I just, okay, maybe I just call it RR. Yeah, RR and R column. So if any of them is equals to 0, then this sum will be greater than 0. So actually I should be taking greater than 0 here. Okay, let's print this out. Zero one zero 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 one. Okay, 010 001 220 202. Yeah, so this part here will be, yeah, so when there's a true, then I will take away -1000. Okay, maybe I increase this number a bit. Not sure whether this will work. If a cell you want to subtract is a 0, yeah, yeah, I guess so. If you want to subtract is a 0, that will be a mistake in the calculation algorithm. Yeah, so it might mean that there are multiple maximums and not, yeah, right, yeah, it might mean that there are multiple maximums, and then what I really want to do is to just make sure that, yeah, maybe I don't need this after all. You're right, yeah, I don't think this is the issue, because if I take this out, I still get the same error, right? Yeah, so let's yeah, maybe there are multiple ways to, yeah, I'm just taking out the highest sum. So if let's say there are more than one highest sum, we might need to choose. We need to think about this further. If there's more than one highest sum, okay, so far we have done until 5 by 5. That's great. Yeah, maybe I will stream tonight again to try to solve the rest. Yeah, but I have a feeling that in order to solve this problem, we need to take, if there's multiple highest sums, we need to sort of choose which is the highest sum that we want to take out. Yeah, I mean somehow it works for the lower problems, but for the higher problems, like, it didn't really work. Not still not too sure why. Is it like there might be some error doing this greedy method, which, I mean, to be honest, the error is not much. You see, there's only it's just only one thing here and this thing here. Yeah, but maybe the layer cake approach may not work that great for higher grade shapes. I'm not too sure. Yeah, but I mean this row count column row sum. mm, I mean I'm quite sure that my row and columns are correct. Okay. Yeah, I have to do a backtracking algorithm. Yeah. So it means that I need to, if let's say at the end of it, it doesn't work, I need to backtrack one. But how do I know which is the step to backtrack? Yeah, then I bet this might be a little tricky. There might be another thing that I'm missing out. So I need to like figure out where, in which cases the layer cake approach doesn't work. Yeah, there might be instances whereby like this up next thing doesn't work. I'm not sure. I'll think about it. Yeah. But anyway, I've got to go. Thanks for watching, and I'll see you all next time. Okay. Yeah. All the best if you are trying to solve this problem. So the layer cake approach can solve until 5 by 5 just by optimizing. Can you do linear algebra using NumPy? Yeah, you are trying to solve multiple equations. Yeah, maybe linear algebra could work. Yeah, I mean because technically you are trying to solve like a few equations at a time. Yeah, definitely. You can try solving it using linear algebra. I think it might work. Yeah, but I'm still trying to make my layer cake approach work though. It's quite nice. Yeah. All right, then see y'all. Bye.